In today's video, we will work through two problems that involve showing the equality of two sets. The first problem deals with a property of intersections and unions of sets, and the second problem is a little bit more interesting, where we have to prove that the image or the range or the set of all possible outputs of a function is some particular set. Let's begin by understanding how to show two sets are equal. We say that two sets A and B are equal when every element in one set is also an element of the other set. So in mathematical terms, we say that two sets A and B are equal if and only if A is a subset of B and B is a subset of A. So basically, they have to be subsets of each other. And how do we show that one set is a subset of another? Let's say, for example, we want to show that A is a subset of B. Then what we would do is we would pick an arbitrary element in A and argue why it must also be an element of B. Showing that one set is a subset of another is a very important skill to master in mathematics, as it shows up in many places. So one of the goals of today's video is actually to get a bit more practice in showing that one set is a subset of another. And we will show both these conditions in order to show that two sets are equal. Let's get started with the first problem. Let's let A, B, and C be sets, and then we have to prove the following result. So this result states that the intersection of a union is the union of the intersections. It captures the distributive property of intersection over union of sets. And again, the left-hand side happens to be a set, and the right-hand happens to be a set, and we're asked to show the equality of two sets. How do we do that? Well, we need to show the inclusion in both ways, as we saw before. So let's begin with the first subset inclusion, where we will show that the left-hand side is a subset of the right-hand side. To do this, we pick an arbitrary element in the left-hand side. So we let X be an element of A intersect B union C. Then what does this mean? Well, remember, the intersection corresponds with AND. So here we can say that X is in A and X is in B union C. Now from B union C, we get that X is in B or X is in C. Remember that the union means or, so we have two cases to consider. Either X is in B or X is in C, or X might possibly be in both, but we'll see that that case might be redundant. Okay, now let's suppose that X is in B. We already have that X is in A from above, so what this means is that X is in both A and B. In other words, X is in A intersect B. Okay, well, we also know that A intersect B is a subset of A intersect B union A intersect C. To see this, well, A intersect B is some set, and the union just adds on some extra stuff. So most definitely, A intersect B is a subset of the right-hand side here. So from this it follows that X is a member of this set, which is exactly the right-hand side of what we wanted to show. But we're not done yet. Now we have to consider what happens when X is an element of C. Well, if X is an element of C, then together with the condition that X is also in A from above, we have that X is in A and C. In other words, X is an element of A intersect C. Well, again, A intersect C is a subset of A intersect C union A intersect B. So it's a subset of this set. And from this, it follows that X is an element of this set, which is again the right-hand side of what we wanted to show. So in all cases, what we see is that whenever we pick an arbitrary element of the left-hand side here, we see that it's also an element of the right-hand side. So this shows that A intersect B union C is a subset of A intersect B union A intersect C. And very briefly, let's discuss why we don't need to cover the case of what happens when X is in both B and C. Well, if X is in both B and C, then either of these cases apply, right? If X is in both B and C, then X is in B, and so therefore we can apply, for example, case B and solve the problem. So therefore we don't actually need to explicitly write that case out, and these two cases are sufficient. Now let's show the other inclusion, that is A intersect B union A intersect C is a subset of A intersect B union C. So again, we pick an arbitrary element of the left-hand side, so let X be an element of this set. Then this means that X is an element of A intersect B, or X is an element of A intersect C. And now once again, we will have to consider what happens when X is in A intersect B, or what happens when X is in A intersect C, or what happens when X is possibly in both? Well, if X happens to be in A intersect B, then that means that X is in A and X is in B. Now, since X is an element of B, and the set B is a subset of B union C, we easily get that X happens to be in B union C. Moreover, since X is in A, and we just established that X is in B union C, then that means that X is in the intersection of these two sets. So we get that X is an element of A intersect B union C, which is exactly the right hand side here. Now let's tackle the other case. What happens when X is an element of A and C, A intersect C? Well, if X is an element of A intersect C, then that means that X is an element of A and X is an element of C, just by definition of intersection. Okay, well, if X is an element of C, and we know that C is a subset of B union C, then we automatically get that X is an element of B union C because X is in C. If X is in C, then it's most definitely in the union of C with B. And now, since X is in A, and we just showed that X is in B union C, we get that X is in both A and B union C. In other words, X is in A intersect B union C. So in all cases, we have that A intersect B union A intersect C is a subset of A intersect B union C. And the way we showed this, again, was we picked an arbitrary element of the left-hand side and we argued why it must be also an element of the right-hand side. Since we have shown inclusion both ways, this actually completes our problem. Here is the full problem written out if anyone wants to see. Now let's begin working on the second problem. In this problem, we're asked to prove that the range or image of the function f of x, which is equal to x plus 1 over x, is the closed interval from 2 to infinity. And this function is defined on the positive real numbers, and its codomain is the set of all real numbers. So once again, this problem is about showing the equality of two sets. The image or the range of a function happens to be a set. It happens to be a set of all possible outputs. And this interval is also a set. So we have to show that two sets are equal. And to do this, we will show that each set is a subset of the other. Let's first show that the image or the range of the function happens to be a subset of the closed interval from 2 to infinity. So this notation where I plug in the entire domain into the function, it's a way to represent the image or the range of a function. And this is basically the set of all outputs of the function f as x runs through the domain. So remember, the domain of this function is the positive real numbers. So this is a collection of all possible outputs for the function f. In other words, this is the image or range of f. And we can denote it using this notation where we plug in the domain into the function itself. Now we will pick an arbitrary element in the range of f. Let's call it y. Then what does that mean? Well, if y is an element of the output space of f, then that means that there is some input from my domain that maps onto y, right? So y is equal to f of x for some input from my domain. My domain is all positive real numbers. Now what we want to show is that this element y is in this set, right? In other words, we want to show that y is bigger than or equal to 2. So what we will do is replace y with its definition. So y is equal to f of x, which is x plus 1 over x for this particular x. So we want this to be bigger than or equal to 2. And now we can actually multiply both sides of this inequality by x. And this is completely fine to do because x is a positive real number. It's from this set. So what we get now is x squared plus 1 is greater than or equal to 2x. And now we will just bring the 2x to the other side. And then this is a perfect square which can be factored into x minus 1 squared is non-negative. Now this is a statement that is true because for any real number a squared is non-negative. So over here, x minus 1 is some real number. When you square it, it's going to be non-negative. So what we have done here in orange is our scratch work or our rough work. Now we can actually write out the formal proof. And in the formal proof, we have to reverse these steps. So we will begin by x minus 1 squared is non-negative. and then we will reverse these steps. We will FOIL this out, then we will bring the 2x to the other side, and then we can divide everything by x and mention that we can do this because x is positive. And on the left hand side here, we have y is bigger than or equal to 2, which is what we wanted to show. And now we're done because we picked an arbitrary element in the image of f, and we argued why that element y is also a member of the interval from 2 to infinity. And so it follows that the image is a subset of this interval. To show the other inclusion, we let y be an arbitrary element of the interval from 2 to infinity. Now what we need to show is that this y is an achievable output for f. So what this means is that we need to argue why there must exist an input x from my domain that maps onto y. Now what we will do is actually solve y is equal to f of x for x. And so what we can do is multiply through by x to get yx is equal to x squared plus 1. And then we can bring the yx to the other side, and we see that this is a quadratic in x. Remember that y is actually a fixed number here, right? Y is some element from 2 to infinity. It's some fixed constant here, and so x is really the variable. Now we can use the quadratic formula to explicitly solve for x. But in this problem, we don't actually have to find the corresponding input. We just need to argue why an input must always exist. And so one way we can do this is, now since this is a quadratic, it will have a real solution if and only if the discriminant, which is b squared minus 4ac, is non-negative. So in this case, the discriminant happens to be y squared minus 4, and we want to check when is this non-negative. So this is a quadratic inequality. We can factor to get y minus 2 times y plus 2 using difference of squares. And to solve this, you can make a number line. You can plot the zeros, which are minus 2 and 2, and then pick test points. So if I pick a test point y is equal to 3, then you'll see that we get a non-negative value. And over here, if I pick, for example, 0, then I get a negative. And if I pick something to the left of minus 2, like for example minus 3, then I get a positive again. So we see that this inequality is satisfied if and only if y is an element of the interval from minus infinity to minus 2, or from 2 to infinity. Well, since our selected y always lies in the interval from 2 to infinity, this condition is always satisfied. And so this shows that y is an element of the image. Lastly, I would like to mention one more thing. Over here, when we had this quadratic, we argued why this quadratic must always have real solutions whenever y is selected in the interval from 2 to infinity. But what we can also do is use the quadratic formula to solve for an explicit value of x that maps onto this value of y. And so the way we would do this is, again, we would use the quadratic formula to solve for x. And so we get two values. Now we need to check which one of these values lies in our domain, because our domain consists of the set of positive real numbers. So let's begin by checking the positive root to see if that satisfies this condition. So the question we're asking is y plus the square root of y squared minus 4 divided by 2 positive? Well, we can multiply both sides by positive 2, and that will preserve the inequality. And then we can bring the square root term to the other side. And so the question we're asking now is y greater than minus the square root of y squared minus 4? And yes, this is true because y is greater than or equal to 2. Well, if y is greater than or equal to 2, then we know the inside is non-negative, and the square root of anything is non-negative, right? So when I put a minus sign up front, this right hand side is always going to be negative. It's always going to be negative. And on the right hand side, well, this is always greater than or equal to 2. So this inequality does hold, and so that means this input x is a valid input. It's from our domain that maps exactly onto y, and you can check that as well. If you simply plug x into the function f, remember that f was x plus 1 over x. So if you do the math, you'll see everything cancels out and you get back to y. And this is by construction because we solve for the explicit x that maps onto y, and so this is just verifying that. And so now you can rewrite this entire proof on the left hand side simply as let y be an arbitrary element from 2 to infinity. Then you can pick x to be this thing, y plus the square root of y squared minus 4 over 2. And then you can justify a little bit more why this lies in the domain, for example by reversing these steps. And then you can just show that when you plug this x into f, you get exactly y. So you can do this work. You can show this work. And so this implies that y is a reachable output. So y is in the image of f. And so that is another way to show that the interval from 2 to infinity is a subset of the image. This brings us to the end of this video, where we worked on 2 problems that deal with showing the equality of 2 sets. I hope you found this video helpful. If you did, you can let me know by leaving a like. If you have any questions, comments, or concerns, please feel free to leave them in the comment section down below. I would be more than happy to respond, and I would encourage you to subscribe for more math videos.